So this is lecture 15 in ordinary differential equations. And what we're going to look at today are sections 5.3 and 5.4, which are both concerned with non-homogeneous linear equations. And we're looking at second order. So homogeneous equation will typically look like y double prime plus p of x y prime plus q of x y equals 0. And the big theorem, which we state but don't prove because it really just takes more mathematics than is required for this class. That is, if p of x and q of x are nice functions, which means just continuous on some open interval a, b, and if x naught is any point in a, b, and k naught and k1 are any real numbers, so this symbol means it's contained in the set. This is contained in the open interval from a to b, contained in real numbers, then there's a solution. There exists a unique solution of the equation y, with y of 0, with y at x naught equal to k naught, and y prime at x naught equal to k1. So this is just the basic theorem we've stated many, many, many times. But this is the homogeneous case. What does the non-homogeneous second order equation look like? Y double prime plus p of x y prime plus q of x y equals some function f of x. So the right-hand side is not 0. And this is sometimes called a forcing function, because in many applications in physics, for example, this is some force applied to something, and this differential equation is just going to describe the motion. So this is a non-homogeneous equation. And there is a similar fundamental existence and uniqueness theorem for this equation. So this says if p of x and q of x, and let me then insert and f of x, because here we have three functions involved in this differential equation. If all three are continuous on some open interval, and if you choose any point in that interval and any two real numbers, k naught and k1, then there's always a unique solution of the initial value problem. So this is, for us, the fundamental existence and uniqueness theorem. If you have a non-homogeneous equation like this equation is called the complementary equation. And if p and q have are numbers, if this is a constant coefficient second order homogeneous equation, we know 100% how to solve it. For non-constant coefficient equations, it's more complicated, but sometimes you're lucky and you can find a solution. And we have the following related theorem. If y sub p is a particular, so the p stands for particular, solution of my equation star. So this is just some solution, any solution, not 0, a non-trivial solution. Any particular solution of this equation. Actually, I don't even have to say that, because if 0 were a solution of this equation, then f of x would be 0, and we would be in the homogeneous case. So if y sub p is a particular solution of this, and if y1 and y2 is a fundamental set of solutions of, let me put 2 stars around this. So I don't have to keep writing it. Then the general solution, that means every solution, of the non-homogeneous equation is y equals a particular solution plus some linear combination of the fundamental set of solutions of the homogeneous equation. So to solve the non-homogeneous equation in general completely, you just have to find one solution, a particular solution, and be able to solve the homogeneous equation. And what I'm going to do today is solve a lot of non-homogeneous equations. Right? That's the whole idea, is to learn the technique of solving these equations. And I'm just going to follow the examples in the book because then it's easier for you when you're studying at home. Right? Any questions so far? So this is example 5.3.1. Y double prime plus y equals 1. So what is a particular solution? Just some function which satisfies this equation. Well, you could just take the constant function 1, because if you differentiate this twice, you get 0, and you get 0 plus 1 equals 1. So that's a particular solution. Right? How did I find that? I don't know. No calculus, I guess. Right? What about the complementary equation? Y double prime plus y equals 0. So we can write down the solutions of that, or you could look at the associated quadratic equation, r squared plus 1 equals 0. The solutions are r equal plus or minus I, which means your fundamental solutions are e to the 0, which is 1, cosine x, y2 is e to the 0 sine x. So this is a pair of solutions to the complementary equation. So the general solution of this equation is y equals 1 plus c1 cosine x plus c2 sine x. So I found a particular solution to the non-homogeneous equation and the general solution, or a fundamental set of solutions, to the complementary equation. Any questions about this? Suppose we have the initial value problem associated with this equation. Suppose we want to find the solution of this equation that satisfies the initial conditions, y of 0 equals 2, y prime of 0 equals 7. So here's y. Y prime is minus c1 sine x plus C2 cosine x. So if you plug in x equals 0, you get 1 plus C1, and that has to equal 2, which means C1 has to equal 1. And y prime of 0 is C2, which has to equal 7, so C2 equals 7. So the particular solution that satisfies the initial conditions is y equals 1 plus cosine x plus 7 sine x. And that's the solution of the initial value problem. All right. Any questions about that? Okay. Let's look at the next example. This is example 5.3.2. Find the general solution of the equation y double prime minus 2y prime plus y equals minus 3 minus x plus x squared. That's the find the general solution. And the second part of the problem will be to solve the initial value problem, where y of 0 is minus 2 and y prime of 0 is 1. So first we have to find a particular solution. And one good guess always, almost always, is if you have a polynomial on the right-hand side, to try a general polynomial as a particular solution and see what happens. We also have to solve the characteristic equation. What is the characteristic equation? That's the homogeneous equation, y double prime minus 2y prime plus y equals 0. The corresponding quadratic is r squared minus 2r plus 1, which is r minus 1 squared equals 0. So there's a double root. So if you let y1 be equal to e to the x and y2 equal x e to the x, this is a fundamental set of solutions to the homogeneous equation. That's what we learned in the previous section, 5.2. And to find a particular solution, let's try y sub p equal to some quadratic. A plus bx plus cx squared. Let's just try that. So if that's y, the second derivative will be b plus 2cx. No, sorry, the first derivative. And the second derivative is 2c. So if we plug this into our equation, we would have the second derivative. Let me just write this down. So yp double prime minus 2y sub p prime plus y sub p. That's equal to what? 2c minus 2b plus 2cx plus y, a plus bx plus cx squared. This is all quadratic. This is, if I collect the terms, let's see, what is the constant term? 2c minus 2b plus a minus 2b plus 2c. And the coefficient of x is b minus 4c. And the coefficient of x squared is c. And I want this to be equal to the right-hand side. Minus 3 minus x plus x squared. And this will work if C is 1, B minus 4C is minus 1, and this is minus 3. Just equate coefficients. So we want to have C equal 1, B minus 4C equals minus 1, and A minus 2B plus 2C is minus 3. So I want to solve these equations for A, B, and C. Well, of course, this says C equals 1. This says 4C is B plus, so this says B is 4C minus 1, but C is 1, so this is 3. And so this is going to be A minus 2B, B is 3, plus 2C, C is 1. So that's A minus 4. So A minus 4 is minus 3. So A is equal to 1. Let me just double check. I have C is equal to 1. B minus 4C is minus 1. So B is 4C minus 1, which is 3. And A minus 2B plus 2C is minus 3. So that's A minus 6 plus 2, which is A minus 4, which means A is equal to 1. So we get a particular solution, Y sub P is A, 1, plus BX, B is 3, plus CX squared, C is 1, plus X squared. So this is a particular solution of my differential equation. And let me just check. So if this is Y, Y double prime, so if this is Y, Y prime is equal to 3 plus 2X, and Y double prime, I differentiate twice, I get 2. So Y double prime minus 2Y prime plus Y is 2 minus 2 times 3 plus 2X plus Y, which is 1 plus 3X plus X squared. This is 2 minus 6 plus 1. That's minus 3. Minus 4X plus 3X minus X plus X squared. So this checks. So this is a particular solution. And my general solution for this differential equation is this plus any linear combination of these two functions. So where I have the differential equation, Y double prime minus 2Y prime plus Y equals minus 3 minus X plus X squared. The general solution is Y equals my particular solution. That's the quadratic I just found. 1 plus 3X plus X squared plus any linear combination of the fundamental set of solutions to the complementary equation. So that's the general solution for this equation. And if I want to solve the initial value problem, which was Y of 0 equals minus 2, and Y prime of 0 equals 1. How do I do that? Well, this is Y. Y prime is 3 plus 2X plus C1 e to the X, plus I differentiate this C2 times e to the X plus X e to the X. That's y prime. So if I evaluate y at 0, I get 1 plus c1. When x is 0, 0, 0, c1 e to the 0 is c1. This is 0. Y of 0 has to equal minus 2. So that tells me c1 is minus 3. Right? That's pretty quick. And y prime of 0, when I plug in x equals 0, I get 3 plus 0 plus c1 plus c2 plus 0. So 3 plus c1 plus c2. And c1 is minus 3. So that's 3 minus 3 plus c2, which is c2. And that's supposed to equal 1. So for the initial value problem, the solution is 1 plus 3x plus x squared plus c1 minus 3e to the x plus c2, which is 1, xe to the x. Or I could write this if I like, 1 plus 3x plus x squared. And if I factor out minus e to the x, 3 minus x. So this or any variation of them is the solution of the initial value problem. Any questions about that? Okay. This is fun, of course, so we'll do some more problems. This is problem example 5.3.3. X squared y double prime plus xy prime minus 4y equals 2x to the fourth. Now, this is not in the form that I like. I like to have the coefficient of y double prime 1. So I want to divide by this x squared. So for x different from 0, or equivalently, either for x in the open interval from 0 to infinity, or x in the open interval from minus infinity to 0, we can divide by x squared. We get y double prime, x over x squared is 1 over x, minus 4 over x squared y, x to the fourth over x squared is x squared. So now I have my equation in this form. Now the complementary equation is y double prime plus 1 over x y prime minus 4 over x squared y equals 0. We already studied this equation. This equation has fundamental solutions, y1 equal to x squared and y2 equals 1 over x squared. Let's just check. If y1 is x squared, y1 prime is 2x, y1 double prime is 2. If I plug into this equation, what do I get? I get 2 plus 1 over x y prime, which is 2x, minus 4 over x squared times x squared. This is 2 plus 2 minus 4, which is known to be 0. So this checks. And what about y1 equal 1 over x squared, or x to the minus 2? So y1 prime is minus 2x to the minus 3. Y1 double prime is 6x to the minus 4. So if I plug into this equation, I get 6x to the minus 4, 6 over x to the 4th, plus 1 over xy prime, which is minus 2 over x cubed, minus 4 over x squared y, 1 over x squared. I get a denominator of x to the 4th in every term. 6 minus 2 minus 4 is 0. So this also checks. So these two functions are solutions of the complementary equation, and neither one is a constant multiple of the other, so they're linearly independent. So they form a fundamental system of solutions. But now we have the problem of finding a particular solution. And we could try a 4th degree polynomial, or to make it even simpler, because I have y prime, and y double prime all occurring here. So experiment, try a particular solution, ax to the 4th. So if I plug that into this equation, what do I get? I can use either this or this. Let me just use this because it's slightly easier. So this is the first derivative, this is the function. The first derivative is 4a x cubed, and the second derivative is 12a x squared. So x squared y double prime plus xy prime minus 4y, that's x squared times 12a x squared plus x times 4a x cubed minus 4 times ax to the 4th. So each of these terms has an a x to the 4th times what? 12 plus 4 minus 4 times 12. 12ax to the 4th, and that's supposed to equal 2x to the 4th, which means 12a is going to be 2, so a is going to be a 6th. So a particular solution will be y sub p equals 1/6 x to the 4th. That's a particular solution to my differential equation. So the general solution will be y equals 1/6 x to the 4th plus c1 x squared plus c2 times 1 over x squared. Okay. Any questions about this? So let me make one more remark. It actually has a fancy name. It is called the principle of superposition. So the superposition principle says the following. Suppose we have y double prime plus p of x y prime plus q of x y equals f1 of x. So this is one non-homogeneous second order equation. And y double prime plus p of x y prime plus q of x y equal f2 is a different second order equation. The left-hand sides are the same, but we have different forcing functions on the right-hand side. And let's say this has a particular solution y sub p1, and this has a particular solution y sub p2. That means if you take this function, you put it into the first equation, it's a solution. If you take this function, you put it into the second equation, it's also a solution. So then the sum of these two is a solution of the differential equation y double prime plus p of x y prime plus q of x y equals f1 of x plus f2 of x. So if you have an equation, a second order non-homogeneous equation, where the right-hand side is the sum of two functions, if you break this up into two problems with one forcing function f1 and the second forcing function f2, and you find particular solutions of these, then their sum is a particular solution of that. And the proof is just straightforward. You plug y1, yp1 plus yp2 into this, and this just falls right out. So let's look at an example. Suppose we have the equation x squared y double prime plus 4x y prime plus 2y equals 2x to the fourth plus 4x squared. So here we have our second order expression. That's this linear second order left-hand side. Something times y double prime, and y. And the right side is a sum of two functions. So the principle of superposition says it's enough to solve separately the two equations x squared y double prime plus 4xy prime plus 2y equals 2x to the fourth, and x squared y double prime plus 4xy prime plus 2y equals 4x squared. Let's find a particular solution. So yeah. Let me just find a particular solution of this. Suppose we let y be ax squared. So y prime is 2ax and y double prime is 2a. So if we plug that into this equation, we get x squared times y double prime, 2ax squared, plus 4x times y prime, which is 2ax. So this is 4x times 2ax, plus 2 times y, ax squared. So this is something times x squared. Actually, it's something times a times x squared. We have 2 plus 8 plus 2, 12 ax squared. And we want that to equal 4x squared. So a equals 4 over 12, or a third. That gives me a particular solution of this non-homogeneous equation, and I can similarly find a particular solution of this, and then I just add them together. Right? That's the principle of superposition. Okay. Any questions about that? Okay. So this is just the preliminary introduction to non-homogeneous equations, and this slightly more general technique, or the somewhat more general technique for solving equations, is yet another example of what is called the method of undetermined coefficients. So this is in section 5.4, which is a very straightforward continuation of what we've been doing. But it gives us a class of second order equations that we should always be able to solve. So for the homogeneous equations, we know everything there is to know about constant coefficient equations, ay double prime plus by prime plus cy equals 0. And I want to consider a second order equation where the coefficients on the left-hand side, a, b, and c, are just constants. A is non-zero, otherwise it wouldn't be second order. And let's say we want to solve this where the right-hand side is an exponential function, e to the ax, times some function g of x, where g of x is a polynomial. So when we started to look at homogeneous second order equations, in section 5.2, we restricted ourselves to constant coefficient ones. And now we're going to look at constant coefficient second order equations where the right-hand side is an exponential or a polynomial or a product of them, right? I mean, if you choose a equals 0, this is just a polynomial. If you choose g of x equal 1, this is just an exponential. And we know how to solve the homogeneous equation. So the question is, how do we find a particular solution of the non-homogeneous equation? And we have a small number of techniques that will always work. So let's start with some simple cases. Suppose we have y double prime minus 7y prime plus 12y is 4e to the 2x. So the complementary equation is y double prime minus 7y prime plus 12y equals 0. And if you look at the quadratic, r squared minus 7r plus 12, that factors. That's r minus 3, r minus 4 equals 0. So for this equation, a fundamental set of solutions is y1 equals e to the 3x, and y2 equals e to the 4x. So solving the complementary equation is easy. But how do we find a particular solution for this? So this doesn't always work, but it often works. Let's just try a solution, a particular solution, which was some constant times e to the 2x. All right. So you have just a pure exponential here. Try e to the 2x. Notice e to the 2x is not a solution of the complementary equation. The solutions of the complementary equation are e to the 3x and e to the 4x, not e to the 2x. if this is our function, the first derivative is 2a e to the 2x, and the second derivative is 4a e to the 2x. So if we substitute into the equation, we can try to solve for a. We get y double prime, 4a e to the 2x, minus 7y prime, 2a e to the 2x, plus 12y a e to the 2x. Let's see, I can factor out e to the 2x and a, and I have 4a to the 2x minus 14a e to the 2x plus 12, which is 16 minus 14. That's 2a e to the 2x. And we want that to be equal to 4e to the 2x. So we have to set a equal to 2. So we get as a particular solution, y sub p is 2 e to the 2x. Let's check. If that's the function, the first derivative is 4e to the 2x. The second derivative is 8e to the 2x. When I plug it into the equation, I get 8e to the 2x minus 7 times 4e to the 2x plus 12, 2e to the 2x. So that's 8 minus 28 plus 24. Is that right? Let me just double check. Okay, y is 2e to the 2x. Y prime is 4e to the 2x. Y double prime is 8e to the 2x. So when I plug it into my equation, I get 8e to the 2x minus 7 times 4e to the 2x plus 12 times 2e to the 2x. So this is all this times e to the 2x. This is 8 minus 20, minus 20 plus 24. That's 4e to the 2x. And lo and behold, that's exactly what it's supposed to be. So for this differential equation, the general solution is y equals a particular solution plus a linear combination of the fundamental solutions of the homogeneous equation. That's it. Now, this works, this method works always, so long as the function on the right-hand side, the forcing function, is not a solution of the homogeneous equation. If it is, then we use the method of undetermined coefficients. Let's look at an example of that. So this is example 5.4.2. We have the differential equation y double prime minus 7y prime plus 12y equals 5e to the 4x. So we saw already that y double prime minus 7y prime plus 12y equals 0 has fundamental solutions. Y1 equals e to the 4x, e to the 3x, and y2 equals e to the 4x. And e to the 4x is the solution of the homogeneous equation, but that's unfortunately what you have on this side, so it couldn't possibly be a solution of the non-homogeneous equation. If you plug in any scalar multiple, constant multiple of e to the 4x, you'll get 0. So let's do something else. Let's try a particular solution, y sub p, which is some function u times e to the 4x. And we want to find a u that gives a solution of the non-homogeneous equation. So if this is my possible solution for this equation, the first derivative is u prime e to the 4x plus 4u e to the 4x. The second derivative is u double prime e to the 4x plus 4u prime e to the 4x plus 4u prime e to the 4x. That's the derivative of this, plus 16u e to the 4x. So I get u double prime plus 8u prime plus 16u e to the 4x. Let's see, yp prime, if I factored out the e to the 4x, was u prime plus 4u e to the 4x. So if I plug these into my equation, y double prime minus 7y prime plus 12y, y double prime is u double prime plus 8u prime plus 16u e to the 4x minus 7 times y prime, which is u prime plus 4u e to the 4x, plus 12y, which is 12u e to the 4x. So I could factor an e to the 4x out of all of this. I get u double prime, 8u prime minus 7u prime is minus u prime, plus 16u minus 28u is minus 12u plus 12u. I just get this. And this is supposed to equal 5 e to the 4x, which means this undetermined, this function to be determined, u, satisfies u double prime minus u prime equals 5. Now, we just need to find a particular solution of this equation. There's actually an easy one you could find. If you let u equal to 5x, u prime is 5, u prime equal minus 5x. Oops. Did I do this right? Minus u prime, 8 minus 7 is plus. So yes, u equal to 5x, u prime equals 5, u double prime equals 0, and 0 plus 5 equals 5. So u equal 5x is the solution of this. If I didn't see this, I could, if I had to solve this equation, I could make it slightly easier by saying, suppose I let v be equal to u prime. So then v prime is u double prime, and this equation is a first order equation now, v prime plus v equal 5. And I can solve this first order equation because I know how to solve first order equations. And I'll still get 5x. So now, unfortunately or fortunately, this is what happens when you're taking a somewhat advanced mathematics class. You really have to know everything that came before. And you have to develop you have to just do lots of problems, lots and lots of problems. And you build up your technique to solve these kinds of equations. So 5x works for this. And so my particular solution is u e to the 4x. That's 5x e to the 4x. Should be a particular solution of this differential equation. And then the general solution is 5x e to the 4x plus c1 e to the 3x plus c2 e to the 4x. Okay. Let me do one or two more problems and then we'll be done. I assigned homework for next week using all the techniques we're talking about today. And the best use of our time perhaps is for you to spend a lot of hours over the weekend working on these kinds of problems, and in class on Monday, ask me to do some of them that you might have difficulty with. Otherwise, I'll pick some at random, but it's really best if you spent the time by yourself first trying to solve the problems. Okay. Any questions? This is a new technique to be learned. Okay, so here's another example. This is example 5.4.3. Y double prime minus 8y prime plus 16y equals 2e to the x to the fourth. Sorry, no e, just 2e to the 4x, a pure exponential. And the complementary equation, y double prime minus 8y prime plus 16y equals 0, has the quadratic equation r squared minus 8r plus 16 equals 0, which is r minus 4 squared, so equals 0. So this has a double root. So the fundamentals, a fundamental set of solutions for this equation is y1 equals e to the 4x and y2 equals xe to the 4x. And unfortunately, e to the 4x is a solution of the homogeneous equation. So to look for a solution, a particular solution, I want to let y sub p be some function u times e to the 4x and see if I can figure out what u has to be. So this is yp. Its first derivative is u prime e to the 4x plus 4u e to the 4x. The second derivative, again, is the second derivative e to the 4x plus 4u prime e to the 4x. Plus, when I differentiate this, I get another 4u prime e to the 4x. That makes this an 8. Plus 4u times 4, 16u e to the 4x. So this is just Calc 1. So let me plug these into my differential equation and see what I get. I get yp double prime minus 8yp prime plus 16y sub p is going to be equal to this. Let me factor out an e to the 4x. I get u double prime plus 8u prime plus 16u minus 8 times y prime. I can again, so this is minus 8 times y prime. I can again factor a 4 prime, e to the 4x out of this. U prime plus 4u e to the 4x plus 16 u e to the 4x. So I have e to the 4x in all of these terms. That's e to the 4x times u double prime plus 8u prime plus 16u minus 8u prime minus 32u plus 16u. So the 8u primes cancel. 16 plus 16 minus 32 is 0. That cancels. So I just get something very simple, u double prime e to the 4x. And that's supposed to equal 2e to the 4x. So I just need a function u where u double prime is equal to 2. So a particular solution of that would be, so if u double prime is 2, u prime is 2x plus some constant. And if I integrate this, I get u is x squared plus rx plus some constant. But I just need to find one solution. I can just let r and s be 0. I can just take u equal x squared because the second derivative is 2. I just need to find one particular solution. So a particular solution is x squared e to the 4x, and the general solution y is x squared e to the 4x plus c1 e to the 4x plus c2x e to the 4x. That now is the general solution of this equation. And if you read carefully through section 5.4, it collects all of these, sort of two techniques very nicely. And, it really, if you put this together, and this actually means it reduces a great deal the amount of work that you have to do. But these examples illustrate what's going on. Suppose you have an equation ay double prime plus by prime plus cy equals some constant times e to the alpha x. Alpha is some number. So there are two cases. If e to the alpha x is not a solution of the complementary equation, then there's always a solution of this non-homogeneous equation of the form y sub p equals a e to the alpha x. And you can find this capital A by plugging this function into this equation and solving for a. Now, the second case is if e to the alpha x is a solution, but x e to the alpha x is not a solution of this equation, then there will be a particular solution of the form y sub p equals a x e to the alpha x. And in the third case, if e to the alpha x and x e to the alpha x are solutions of this homogeneous equation, then y sub p equals a x squared e to the alpha x will be a solution. And again, all you do is you plug these three possible forms of solutions into the differential equation, and you can solve for a. Okay. Okay. Let's look at one or two more examples, or maybe one more example, because I don't want to get through too much. Suppose we have an equation y double prime minus 3y prime plus 2y is some exponential, say e to the 3x, times a polynomial, minus 1 plus 2x plus x squared. Now, again, if we look at the homogeneous equation, the complementary equation, this has constant coefficients. We solve it by solving the quadratic. And this factors, this is r minus 1 times r minus 2 equals 0. So y1 equal e to the x, y2 equal e to the 2x. These are solutions of the homogeneous equation. Now, to find the solution of the inhomogeneous equation, let's try looking for a particular solution of the form something u times e to the 3x. Let's try that and see what happens. Solve for u if we can. That's the whole idea. So this is the function. Its derivative is u prime e to the 3x plus 3u e to the 3x. The second derivative is u double prime e to the 3x plus 3u prime e to the 3x. That's the derivative of this. The derivative of this is 3u e to the 3x plus 9, 3 times 3, 9u e to the 3x. So this is u double prime plus, this should be a prime here, plus 6u prime plus 9u e to the 3x. So if we plug this into the left-hand side of this equation, yp double prime minus 3y prime plus 2y, that's e to the 3x times this, minus 3 times y sub p prime. If I factor out the e to the 3x, see this was u double prime, u prime plus 3u e to the 3x. So if I multiply this by 3 or by minus 3, I get minus 3 times u prime plus 3u plus 2 times y plus 2u, all times e to the 3x. So this is e to the 3x times u double prime. I have 6u minus 6u prime minus 3u prime plus 3u prime plus 9 minus 9 plus 2 2u. And this is supposed to equal e to the 3x times minus 1 plus 2x plus x squared. So if I cancel the e to the 3x's, my function u satisfies the equation u double prime plus 3u prime plus 2u is this polynomial. And when I have a differential equation of this form where the right-hand side is a polynomial, I look for a solution, a particular solution, which is just a polynomial of the same degree, quadratic, say a plus bx plus cx squared. Let me see if I can find a, b, and c that solve this equation. So for this, the first derivative is b plus 2cx, and the second derivative is 2c. So if I plug into this, I get 2c plus 3u prime, 3 times b plus 2cx plus 2 times u, a plus bx plus cx squared. So this is 2c plus 3b plus 2u, 2, plus 2a, that's my constant term. Coefficient of x is 6c plus 2bx plus cx squared. And that's supposed to equal minus 1 plus 2x plus x squared. And now I can solve. This says c is equal to 1. This is equal to 2. If c is 1, so 6 plus 2b equals 2. 2b equals minus 4. So b is equal to -2. And right, if C is 1, 6 plus 2B equals 2, 2B equals -4, B is -2. 2C plus 3B, this is 2 minus 6, that's -4 plus 2A equals -1. So 2A equals 3. So A equals 2B plus 3B, 2A plus 3B plus 2C has to equal the constant term -1. 6C plus 2B has to equal the coefficient of X, which is 2. And C, oops, 2C, forgot, 2 times that, 2C. So 2C is 1. So C is a half, and I can solve for A and B, and I've solved this equation. Right? That is the story for today. So what I've been discussing is in chapter 5, sections 3 and 4 on non-homogeneous second order equations. And I assigned a few problems for next week for homework, but really the more you do, the better. I really encourage you to spend a lot of time learning these techniques. Okay. Any questions about this or about anything else that we're doing? If not, then we are done for the morning. And today is Wednesday, so have a good weekend and see you on Monday. Bye all.